Welcome back. In this video, we are going to solve example 6.17 that is taken from chapter number 6 bending and book name is Mechanics of Material by RC Hibbeler 9th edition. And the topic is composite beam. So statement is a composite beam is made of wood and reinforced with a steel strap located on its bottom side. It has the cross-sectional shown in this figure. If the beam is subjected to bending moment of 2 kN into meter, determine the normal stress at point B and C. Take E of wood is 12 gigapascal and E of steel is 200 gigapascal. So you can see this is the cross section of the beam that is shown. This portion is wood and there is a steel strap located at the bottom, and it is subjected to a movement of 2 kilonewton into meter. So you have to determine the stress bending or normal stress at point B and bending or normal stress at point C. So let's start with the solution. As this is a composite beam, so it is very difficult to find the neutral axis for this beam. For that, we will convert this composite beam into a beam that is made up of either this completely with steel or with wood. So what we will do is that we will convert this beam into whole steel beam. You can also convert it into totally wood. So for that, what we will do is that we will calculate N and we will take the modulus of elasticity of steel at the bottom. So we will write this E of steel, E of wood. So E of wood divided by E of steel. So 12 gigapascal divided by, we will take this 200 gigapascal. So when you get this N, so N will be equal to 0.06. Now, although the choice is arbitrary, here we will transform the section into one made entirely of steel. Since steel has greater stiffness, that is why we take E of steel in the denominator, and numerator we have E of wood. The width of the wood will be reduced to equivalent width for the steel. So we are not going to change the height of this wood beam, so only the width of this wood beam will be reduced by a factor of 0.06. So I can write it that now width of this steel that is replaced by this wood will be equal to N into B of wood. So from here you can write 0.06. Now width of wood is 150. So I can write 150 millimeter. So when you calculate it, it will be 9 millimeter. So we will convert this beam into entirely made up of steel. So you can see this width is, this is initial strap which has a thickness of 20 millimeter. This width of steel strap is 150 millimeter. Now for wood, we can say the height will be remain same 150, but width will change to 9 millimeter. So it will be like this. It will be like this. So this width will be 9 millimeter. This will be 9 millimeter, and this height will be 150. So what we have done is that we have converted this composite beam into beam that is made up of purely steel. So I can write it steel beam. Now what we will do is that, as we know that stress is equal to movement into Y divided by I, and there is a negative sign. So we will first find I, which is the section property, and for section property we must know the location of centroidal axis or neutral axis. So we will find this location of neutral axis y bar, which will be equal to y dash bar into A divided by sum of area. So this is your first and this is your second portion. So I can elaborate this formula as this is y1 dash into a1 plus y2 dash into a2 divided by sum of area, which is a1 plus a2. Okay, so now what is a1? So a1 is the area of this section. So you can see it is 150 by 20 millimeter. So I can write a1 is 150. So in meter, 150 is 0.150 and 20 millimeter is 0.02. What is a2? So a2 is the cross-sectional area of this portion, which is 9 by 50, 150. So I can write it, a2 is 9 millimeter, which is 0.009 multiplied by length is 0.150 meter. So the unit here will be square meter and here it will also square meter. Now what is y1 dash? So y1 dash is distance from reference line till the mid of first section. So if I take this as a reference line, so I will write here that we will take this bottom line as a reference line. So from reference line till the mid of first section, this will be y1 dash. So y1 dash is equal to 20 divided by 2, which is equal to 10 millimeter. So I can write y1 dash is 10 millimeter or 0.010 meter. Now what is y2 dash? So y2 dash is distance from this reference line till the mid of the second section. So mid of the second will be at a distance of 150 divided by 2 plus this distance, which will be 20. So 75 plus 20 is 95 millimeter. So let me show you over here. This will be y2 dash. From this till this reference line, this will be y2 dash. Okay, and that is 95 millimeter. In meter it is 0.095 meter. Now you have all the values, just plug it in this formula. So you will get y dash, our location of centroidal axis or neutral axis from the baseline will be equal to y1 dash is 0.01 multiplied by area is 0.02 into 0.150 plus what is y2 dash, which is 0.095 multiplied by a2. A2 is 0.009 into 0.150, and we will divide this whole term by area a1 plus a2. So a1 is 0.150 multiplied by 0.02 plus 0.009 multiplied by 0.150. Okay, so when you solve this, you will get it 0.03638 meter, or you can see y bar is 36.38 millimeter from the baseline. So if I draw it like so, it will be somewhere here. Let this will be your location of neutral axis. So this will be the distance from this baseline till this will be y dash bar. Okay, I will write the value over here. This is 36.38 millimeter. Now this remaining distance from this top till the neutral axis will be this one. Let me show you over here, and this distance will be 170 minus this 36.38, and that will be equal to 133.62 from neutral axis till top, this distance. Okay, so what we will do, we will now find the moment of inertia I, and we know that by using parallel axis theorem, I will be equal to sum of I dash plus AD square. So if I expand it, what does it mean? That I dash 1 plus A1 D1 square plus I2 dash plus A2 D2 square. Okay, Now what is I1? So for this one we will take the moment of inertia about this neutral axis. So it can be written as 1 over 12 B1 H1 cube plus area, which is equal to B1 H1 into D1 square. Clear? This will be I1 dash plus I2 dash is for this section. So you can see it will be 1 over 12 B2 H2 cube plus area, which is equal to B2 H2 into D2 square. Okay. Now you will plug in the value 1 over 12. What is B1? So B1 is this 150 and height is 20 millimeter. So in meter it is 0.150 and height is 0.02. So I can use it will be equal to 0.150 multiplied by height is 0.02 whole cube plus area, which is 0.150 multiplied by 0.02. And what is D1? So D1 is distance from neutral axis till the mid of first section. So you can see this distance will be equal to y dash minus 15. So y dash minus 15. No, not 15, sorry. This is y dash, which is 36.38 and half of 20 is 10. So I can write it 36 in meter is 0.03638 minus 10 is 0.01 and it will be square. Okay. Plus, now we will use this term one for the second one. So base, you can see that base is 9 and height is 150 millimeter. So I can write 1 over 12 base is 0.009 and height is 0.150 whole cube plus area 0.09 into 0.150. And what is D2 square? So D2 square is distance from neutral axis till the mid of second section. So this will be D2. And this can be obtained if you take 0.095 minus this distance. So as we have seen that this y2 dash is 95. So 95 minus this y dash will give you D2 dash. D2. So D2 is 0.095 minus 0.03638 whole square. Okay. Let me clear it and let me write it correctly. I will write it downward. So it will be 0.095 minus 0.03638 whole square. Okay. Now when you solve this, you will get this total moment of inertia of the beam about neutral axis, and it comes out to be 9.358 into 10 to the power minus 6 meter power 4. Okay. Once you get this value, so what you will do is that you will see that this was your point B and this was your point C. So we will do what we will do is that we will find normal stress. So apply Flexural formula and this formula to get normal stress at B dash or B and C. So for B, we can find sigma B dash is equal to minus moment into YB divided by I. Okay. So the point that is taken on this is, let's say this is B dash. So we'll find B dash. So B dash will be this one. Now minus moment value is 2 kilonewton, and what is YB? So YB is distance from neutral axis till point B, and you can see this distance is 133. This distance is 133.62. How we get this 170 minus 36.3? Okay, So I can write it minus 2 kilonewton. So 2 into 10 to the power 3 multiplied by YB is 1. What I have shown you is 133.62. Either you can write this or this. So both will be 6. So according to, I will write it as it is given in the book, that it is 0.170 minus 0.03638 divided by I. And I is 9.358 into 10 to the power minus 6. So when you solve this, you will get it 28.6 megapascal, and that will be negative. Also, you can see that sigma B dash is 28.6 megapascal, and that is at point B is in compression. Now for point C, we get sigma C is minus m into YC divided by I. So again, minus m is 2 into 10 to the power 3. What is Y? So Y is C, distance from neutral axis till point C, which is 20 millimeter. Clear? Not 20 millimeter, sorry. This is 36.38 millimeter, and it is downward, so it will be negative. So I can write it minus 0.03638 divided by I, and I is 9.358 into 10 to the power minus 6. And when you solve this, you will get 7.78 megapascal. Since your point stress at point sigma C is positive, so 7.78 megapascal, and that will be in tension. Okay. Now what we will do is that if I represent this stress on the beam shown over here like this, there, so it will be that this is the beam. So you can see if this is the neutral axis, location of the neutral axis. So at point C, at point B dash, this was your point B. So at point B dash, we have compression, so it will be like this. And in neutral axis, we know that the stress will be 0. So till this, it will be, all will be in compression. Clear? This will be in compression. And at point C, that will be in tension. So the stress at point C will be in like this. This will be the stress at point C. What is the magnitude over here? That is 28.6 megapascal, and the arrow shows toward point B is that they are in compression, and at point C they are in tension, and this is 7.78 megapascal. So what I do is that I will make them a little bit shorter because the amplitude is less. So this is your point C, and the stress is tensile, so it will be like this, and the stress at this point C is 7.78 megapascal. Okay, and from this neutral axis, you can see that if you want to calculate the stress at point this, I will show you that this will be 3.50 megapascal. How you will find them, I will show you in a while. So this will be the stress in this portion here, and if you join them, it will be like this. Okay, so from this, it will be, the stress will be like this. Clear? How you will find this 3.50 megapascal? So if you put distance in this formula, sigma is equal to minus m into y divided by I. So distance from neutral axis till this point. So this will be 36.38 minus 20 will give you this distance. Just plug it in this formula. You will get this stress will be equal to 3.50 megapascal. So this is the distribution of stress when the beam is completely made up of this steel beam. Now we are going to back, and as we know that N was equal to E of wood divided by E of steel, and that was 0.06. So the stress at point B, that stress at point B for wood, that will be equal to 0.06 times what was stress at point B dash. This was 28.6. So 28.6 megapascal. So when you calculate, it will be 1.71 megapascal. Similarly, stress at point C for wood, it will be equal to 0. At C, that is already steel, clear, for the wood, sorry, for this composite beam. So it will remain the same. Let me show you. This will be not, it will be same, which was for, and that was 7.78 megapascal. Also, you will see that at the junction of this wood and steel, the stress was 3.50 megapascal. So again, what at steel and wood portion, the stress in wood will be, stress is, that will be 0.06 multiplied by 3.50, and when you calculate it, it will be equal to 0.210 megapascal, and then it will move toward, in steel it will be 3.50. So what if I represent this on the composite beam? So this beam will be like this will be wood, and this portion is steel strap, clear? This is the steel strap, and this was the neutral axis or centroidal axis that was calculated for this beam that is made up of pure steel. So we can see that at point B, this was your point B. I will choose black color. This was your point B, and this was your point C. So as point B was in compression, so for wood this will be this one, it will be 1 point. If I draw it like this, so this will be like, the stress distribution will be like this one. All the line will be parallel, and you can see till the neutral point axis, it will be like this. This will be in the wood portion, will be in compression, clear? And then there will be extension till this point. Okay, this till this wood point, and at this point you can see the stress will be 0.210. So 0.210 megapascal. So it will be like this. Again, you can see at this junction you have the steel started. So what we will do is that you can see this line will move ahead like this here. So for steel junction, this will be the stress, and this point at this point the magnitude will be 3.50 megapascal at this point, and in lower portion it will be 7.78. So if I draw it like this, so 7.78. So your stress will change from this till this. It will be like this. Okay. So what we can say that this will be the stress distribution in steel portion. So that is for composite beam. Okay, the stress is 1.71 megapascal. So our answer is stress at point B is 1.71 megapascal, and stress at point C is 7.78 megapascal for this composite beam. This is in compression and this is in tension, and that is answer of our this question. And this was all about this problem example 6.17. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. This problem was explained and was requested due to a subscriber who requested me to explain this problem in the video. So it is dedicated to him. Thank you.